In this video, we're going to introduce polynomial long division and the division algorithm. So, if we just remember doing division back in grade school, we always found a quotient and a remainder. So, for example, if we divide the 47 by 6 here, we get 6 goes into 47 7 times, and we have a remainder of 5 left over. So one way we could actually write this is that 47 is equal to 7 times 6 plus the 5. So notice we've got the quotient of 7 multiplied by what we divided by, and then added the remainder on at the end. Okay. When we do this for integers, we always make sure that our remainder is non-negative. Certainly this is not unique here. We could have also done 47 as 8 times 6 minus 1. This would be another way to write it in a similar form. But that minus 1 would tell us that the remainder is negative. And when we did remainders, we always wanted to make sure that remainder was not negative. Could be 0. The number could go evenly in. But it definitely couldn't be negative. And the other thing we noticed is that this number needed to be strictly less than what we were dividing by. Right? It's a remainder. It's what's left over when we try to put that 6 into 47, right? We wouldn't want this remainder to be, say, 11, because I could put 6 into it one more time. All right, so when we make sure that the remainder is not negative and the remainder is also strictly less than what we're dividing by, that makes our answer unique. So this is the only way to write 47 when dividing by 6 in this fashion, making sure we satisfy those two conditions. This is an example of what's called the division algorithm for integers. Now we're going to extend this division algorithm to polynomials. So let's suppose that we have f of x and p of x, and we're going to divide f of x by the p of x. Then there's going to be these unique polynomials, q of x and r of x, so standing for the quotient and the remainder, so that we can write f of x in that similar form that we have for integers up here. We can write f of x as the quotient times p of x plus the remainder r of x, or either the remainder is 0, so p of x evenly divides f of x, or the degree of r of x is strictly less than the degree of p of x. So just like I mentioned before, the q of x is called the quotient and the r of x is called the remainder. So let's do an example of rewriting this polynomial, the 5x to the fourth minus 7x cubed plus 2x squared minus 8x plus 6, as after being divided by this x squared minus x minus 7 in that form that we just saw for the division algorithm for polynomials. So the way I set this up is what looks like long division. So I've written the polynomial that we're dividing into under the division bar and what we're dividing by outside the division, just so like you would do long division of integers. One thing to notice is that you want to make sure that, well, you don't have to, but it's easier if you make your degrees of your terms decreasing here as well as here. And just for aesthetic reasons, it's nicer to put zeros in each of these spots where there's not a term. So for example, if the x cubed were missing here, I would write a 0x cubed here just as a placeholder, if you will. All right, so the first step here is I notice that my x squared, that degree is certainly less than the degree of the 5x to the fourth. So I'm going to divide it into. So I ask myself, what do I need to multiply x squared by to get 5x to the fourth? Well, I need to multiply the x squared by 5x squared. So I take this 5x squared here, and I write it up here above the 2x squared. I'm going to multiply that by the entire polynomial that we're dividing by. When we do that, we get 5x to the fourth minus 5x cubed minus 35x squared. Just like what you do when you do division for integers, right? You figure out how many times this goes into that piece of the integer, and then you write how many times that is, and then you multiply and you subtract. It's the same type of process. All right, so we're going to subtract down. Now again, I'm going to subtract everything. So I do 5x squared minus a 5x to the fourth minus 5x to the fourth. That gives me 0. Negative 7x cubed minus a minus. You got to make sure this minus sign gets distributed to everything. It's negative 7x cubed. It ends up being plus 5x cubed. Gives us a negative 2x cubed. 2x squared minus a minus 35x squared gives us 37x squared. I look at this 2x cubed. It still has a degree that's too big because we're trying to get less than this degree here. How many times does x squared go into negative 2x cubed? Or what do I need to multiply x squared by to get negative 2x cubed? That's a negative 2x. We take that negative 2x and distribute it through. We get negative 2x cubed plus 2x squared plus 14x. Again, we subtract down. Negative 2x cubed minus a minus 2x cubed gives me 0. 37x squared minus 2x squared gives me 35x squared. Negative 8x minus 14x gives me negative 22x. Bring down the 6. The 35x squared still has a degree that's not less than this, so I ask myself, what do I need to multiply x squared by to give me 35x squared? That would be 35. Distribute the 35 through again. We get 35x squared minus 35x minus 245. Subtracting down again gives us 13x plus 251. Now I've got a degree here for this polynomial. The degree of this polynomial is less than the degree of that polynomial. So I'm done. So that means that we can rewrite our original polynomial as 5x squared minus 2x plus 35, the quotient, times the x squared minus x minus 7, what we're dividing by, and then plus the remainder, which is 13x plus 251. We could also write it as a fraction, basically dividing both sides by this x squared minus x minus 7. Here would be the fraction, and then we would just have the quotient plus the remainder over what we divided by. Many times, especially throughout this chapter, we're going to want to divide by a linear polynomial, or said another way, a polynomial that has degree 1. So for example here, let's suppose we want to divide 4x cubed minus 7x squared plus 8x minus 12 by x minus 3. Here's what the process looks like when you go through the division. I need to multiply x by 4x squared to get 4x cubed. Distribute the 4x squared through to get 4x squared minus 12x squared. There should be a 4x cubed minus 12x squared. There should be a squared term here. It's a typo. Subtract down. We get positive 5x squared. Bring the 8x down. Now ask yourself, what do I need to multiply x by to get 5x squared? Well, that would be 5x. Distribute through again. Subtract. What do I need to multiply x by to get 23x? Well, that would be a 23. Multiply through and subtract again. We end up with 57 at the very, very end. So if I look at what this fraction looks like then, here's the quotient, 4x squared plus 5x minus, or plus 23, and then we take the remainder over what we divided by, the x minus 3. So there's a couple of things to note from that previous example. The first thing that we notice is that if we actually plug in 3 into the function, we get 57. Notice there is a relationship here. Look at this is the 3. If I plug in 3, I get 57 out. This is what we refer to as the remainder theorem. The remainder theorem says that if you divide a polynomial by x minus a, then the remainder is what you get when you plug a into the polynomial. The other thing to notice is that really we don't have to keep track of all the x's as we go along. We only really need to keep track of certain coefficients. So when we wrote down the second 4x squared term, the second 5x squared term, and the second 23x squared, the second 23x term, we really didn't need to, right? Let's go back to that example. I don't really need to write this 4x cubed down. I don't need to write the 5x squared down. I don't need to write the 23x down because they're just subtracting out and becoming 0. I know what's going to happen with those. Writing them down is a waste of time. The important numbers that we need to write down are the ones that we are subtracting and getting a non-zero answer from. that negative 12, the negative 15, and the negative 69. Where did those come from? Well, the negative 12 came from the 4 times the negative 3. The negative 15 came from the 5 times the negative 3. The negative 69 came from the 23 times the negative 3. So notice each of these, the 12, the 15, the 69, are all those multiples when we end up on our quotient. And then the subtractions we need to keep track of, those non-zero answers. So this is a process that we refer to as synthetic division. So here's how synthetic division works. We're dividing by x minus 3 in that example, so I put a 3 up in the upper left-hand corner here. Across the top, we put in the coefficients for the polynomial that we're dividing into. And make sure we put in zeros if there are any terms that are missing. So in this case, we had a 4x cubed minus 7x squared plus 8x minus 12. So here go the steps. The first thing is we're just going to rewrite the 4. 4 times 3 gives us 12. Now we're going to add. Negative 7 plus 12 equals 5. Multiply the 3 and the 5 gives us 15. Add down the column. 8 plus 15 is 23. Multiply 3 and 23 gives us 69. Add down the column, we get 57. So notice that the 57 again is that remainder term that we saw, but also notice the 4, the 5, and the 23. Those numbers are the coefficients in the quotient polynomial. So we started with the 4x cubed. When we divide by a linear term, that means we're definitely going to get a 4x squared. So we can write down that we have a 4x squared plus 5x plus 23 as the quotient, and 57 is the remainder. You can write that right down from the synthetic division. Let's do another example of synthetic division. So let's say we want to divide the 2x to the 4th minus 7x squared plus 3x plus 2 by x plus 2. Alright, so again, this is x minus a minus 2, so we'll put the negative 2 up in the left-hand corner. The coefficients here start at 2 for the x to the 4th. The x cubed term is missing, so I put a 0 in for the x cubed, minus 7, a 3, and a 2. All right, so the first step is bring it down. Second step is multiply. Then we add. Then we multiply. Then we add. Then we multiply. Then we add. And finally, we multiply and add. So we notice we have a 0 here. So it tells us the remainder is 0. So I can rewrite the fraction as 2x cubed minus 4x squared plus x plus 1. And there is no remainder to worry about. It also means that negative 2 is a 0 of the original polynomial, because when we plugged in negative 2, we got 0 out. So we can use synthetic division not only to give us quotients and remainders, but we can also test whether or not something is a 0. So in this example, we're being asked, is 2 minus 3i a root of the polynomial x cubed minus 3x squared plus 9x plus 13? So we'll run through the synthetic division process. We can do synthetic division with a complex number just as easily as we can do synthetic division with a real number. And it's the same process. We've written down the coefficients on the polynomial. Bring down the first one, do the multiplication. Add down. Negative 3 plus 2 gives us negative 1 minus 3i. Move across. 9 minus 11 gives me negative 2, and then a minus 3i. And finally, if we take 2 minus 3i times negative 2 minus 3i, we get negative 13. If you multiply all that out and simplify, 13 minus 13 is 0. So since that remainder turned out to be 0, we conclude that that 2 minus 3i really is a 0 of the given polynomial.